Hello everyone and welcome to our deep learning road trip for physicists. I am thrilled you are here. Grab a coffee, lean back, and let's build a neural network from the ground up. What you see on screen right now is a very simple network. Two input values, x1 and x2, flow into two hidden nodes and finally produce one output z. The straight arrows represent linear combinations, while the little circles are the hidden nodes. Each arrow carries a weight w, and every circle adds a bias b. Together they form what mathematicians call an affine transformation. Let's read that out in plain English. Vector y equals bold w times vector x plus vector b. Line by line, the first hidden node, y1, is w11 times x1 plus w12 times x2 plus b1. The second hidden node, y2, is w21 times x1 plus w22 times x2 plus b2. That is exactly what the arrows and circles in the picture are doing. Next, the two hidden outputs are mixed once more. Weights C1 and C2 scale Y1 and Y2, and a final bias D shifts the result. Put differently, multiple affine steps in a row collapse into, guess what, one big affine step. That's why a purely linear network can only draw straight lines in data space. Time for some non-linearity. On screen you now see the same network, but each hidden node is wearing a new hat labeled sigma. Sigma is our activation function, and it bends straight lines into anything we like, curves, steps, or wiggles. Sigma of vector y simply means feed y1 through sigma, feed y2 through the same sigma, and pack the results back into a vector. Now listen to the magic. Weight C1 scales sigma of the first hidden node, weight C2 scales sigma of the second, and we add d. Because sigma is non-linear, we can no longer squash everything into one straight line, exactly what we want. Here are three popular activation functions. First, ReLU passes positive numbers straight through and zeroes out negatives. Second, the sigmoid squeezes everything between 0 and 1. Third, the hyperbolic tangent, or tan h, stretches from -1 to +1. Pick your favorite. Upper left ReLU is fast and usually wins. Alright, here is the forward pass slogan in one line. Vector z equals sigma of bold w times vector x plus vector b. Every node in every layer does exactly that. Stack enough of them and the network can model jaw-dropping complexity. The picture you see shows a smooth curve hugging noisy data, pairs of xy values. That is a regression challenge, modeling a temperature, energy, or brightness distribution. To get the curve, our network should predict for a given input, x a continuous value z. How do we adapt the weight and bias parameters of the network to follow the data points? Take each pair of points, xi and yi. Build the sum of squared differences between the network output z in response to xi and the actual expected value yi. This is the mean square error that we minimize when training the network. In other words, we tweak every weight w and every bias b of all network nodes so the predicted curve approaches the data points as closely as possible. Still on the same screen, the lower right panel shows two clouds of symbols with a neat separation line that is classification. Same network idea, but now we push the final output through a sigmoid and call everything above 0.5 signal and everything below background. Add more output nodes, and you can classify animals, particles, or even galaxies into many categories. Finally, you might wonder, can a network really approximate any function I dream of? Enter the universal approximation theorem. It says that a feed-forward network with just one hidden layer and a finite number of nodes can mimic any continuous function on a bounded set as closely as you wish. Pretty reassuring, right? Of course, the theorem does not tell us how many nodes we need or how hard training will be, but it promises the job is possible. And that wraps up our whirlwind tour. Affine transformations with weights and biases, hidden nodes that apply an activation function, a forward pass that predicts outputs, regression for continuous targets, classification for discrete labels, and the universal guarantee that, in theory, we can learn it all. Thanks a ton for watching. If you enjoyed the ride, give us a thumbs up, hit subscribe, and share the physics love. See you in the next video. Until then, keep exploring and stay curious.